Hello and welcome to my Nand Gate tutorial, and this is the Nand Gate I used, and I ended up using it for a 4-bit adder as shown down here. So to get into it, I'll just kind of go over the basics of the circuitry, why I made some decisions, and how it works. So the first decision I made when it came to Nand Gates was how the output should be. So previously I made a design where a 1 was represented by a conveyor belt that had a full amount of plates on it, and a 0 would be represented by an empty conveyor belt. Now this worked well for making a NAND gate, however the latency between different gates was very high, and to show you what I mean, I have this demonstration here. So one problem with the design was the transmission. So if I was changing from a 0 to a 1, let me pull up a conveyor belt here, it would take a very long time for things to transmit, for the signal to propagate. So as you can see, it is taking a very long time for this output to reach the input of the next gate. So my solution was instead to have it based on movement, where a 1 is represented by a moving conveyor belt, and a 0 is recommended by a backed up conveyor belt. Now, one thing that is interesting about this design is this flips where the cause and effect is coming from. So with a normal design, right, you have your output of the first gate to the input of another gate, and it goes from left to right. One thing with this design is it follows backwards from the conveyor belt convention. So what do I mean by this? Well, if I were to have a signal propagating, so right now this signal would be considered a 0, it's not moving. But if I add a conveyor belt, now it is moving. So this would actually be the output of the gate. So this one conveyor belt, whether this is present or not, controls whether this line is moving. So if I remove it, it stops, and that propagates backwards near instantaneously. So just to show that again, we have the conveyor belt moving, it starts moving all in sync. So that means that data is propagated instantly across this wire versus this wire. Another way to represent this is with thinking of this as a pipe of water. So the traditional gate input and output, you would have your source of water, and this would be your output, and this would be your input, and you'd wait for the water to flow towards the input of the next gate, where then it would be received. With this design, it's more of a dam. So if I were to draw it out, this would be more like the pipe is always filled with water. Let's just finish drawing. So the pipe is always filled with water. However, we have a break in the dam. We have a blockade. So if this is blocked, we have no flow of the water. Water can no longer propagate this direction. And this would be the new input. This would be the output, kind of output input, right? So here, let's draw this a bit better. The blockade would actually be the output. And what information would travel backwards through the pipe, right? So if I were to remove the dam, water would then start flowing. So more or less, I'm testing whether there is flow or there isn't flow based on the status of either a dam being present or not. But more or less, information is flowing against the current. Now, the interesting part, how do you make an NAND gate out of this information? And in this case, how do you make one without the need of resource production or researchers or coal power plants to get rid of resources. So this design is covering two inputs. So as I stated earlier, the inputs will be opposite of flow. So this is actually our input line. So if I remove, so right now both are flowing, so that's a 1 bit. If I remove it, that becomes a 0 bit. It is no longer flowing. And as you can see, that propagates near instantly. And then our output is the same way. This is actually our output. So if this line is flowing downwards, that tells us it is a 1. If it is not flowing, like in this case, it is a 0. Some other necessary parts of this is two things. We need a power rail, which I like to call VCC, to follow some electrical engineering terms. So this, we need a constant source. Actually, we don't even need it here, but in general, we need a constant source. We do need it, but this would normally come from another gate, right? This is our input to the Nand Gate. And then we also need a voltage sink, a current sink, I should say. So this would be our VDD. So we kind of just want to scrap whatever comes through here. Again, all we care about is there movement across this line, and then our outputs, which is this line and this line. So the main question is, how does this work? Well, there's an interesting mechanic of Builderment with these robot arms. So these robot arms, as you know, you can set to a specific resource. In this case, I have these arms set to these wooden frames. And these arms up here are all set to iron plates. So what ends up happening is, if there are frames going through these lines, then the plates cannot propagate through, effectively turning the signal off, right? There's no flow. However, and this may take a while, I noticed the computer version of Builderment is a little slower compared to mobile. Here, I'll turn both of these off just for demonstration. So if we no longer have frames coming in, well, what ends up happening? These two sets of plates with these robot arms are no longer blocked, allowing a free flow of plates, which turns this input on. And same with this input. And this is what I would like to call fan out as well. So more or less, given any output, we can determine how many lines we have output. So for example, this could be fed into a different gate along with this one, or we could even add a third, a fourth, or a fifth. We have an arbitrary amount of fan out. So this is infinitely expandable if you need it to be input into other circuits. So now that it's updated, we can see that because there are no wood frames propagating, we have a free flow of plates. So that is the main portion of this circuit of how the output is determined, right? And these storage heaters are for a buffer, right? So we want these robot arms to always be running. So these storages allow for a little bit of a buffer where it allows this line down here to be full. And again, this is our VDD line. We don't care about what happens after this point. But it can be recycled if you make a large circuit. So that covers kind of the output portion of it, right? So this is now on, and we could have a different circuit up here that checks if this is on or off. So onto the input side of things. Well, how does this work? Well, if we are backed up, then nothing flows. So what we have here, let's run one as 1, but this one as 0, just for a comparison perspective here. So what we can see here is when we have a free flow of plates, these frames end up propagating. So these are inserted up here, and these are inserted in every other position to a plate line. So more or less I'm taking a full conveyor belt and I'm splitting it into two portions, and those can be picked up by these robot arms here. So more or less, if this line is on, we are grabbing frames. That's the simple bit of it. So then how does that equate to a NAND gate? Well, because only one of these lines is on, we are only getting a half full belt of frames. And these robot arms like filling the little gaps. So we actually, even though we have frames coming through, we still have enough gaps to allow a free flow through our output. And which would equate to a 1. And then if both inputs are on, what ends up happening? Well, now we will get a full amount of frames flowing through here, blocking the signal entirely. So each line kind of contributes to half, and it only turns off if both halves are active. Okay, now here's where this can be implemented to an extreme. So what I have here is 4 full bit adders connected together. So if we go down here, here's my little display for it. So right now we are adding 0 plus 0 equals 0. So if we wanted to do a different input, we just delete some of the belts here, stopping the flow. So remember, flow is what determines our bits. So if I remove this belt and this belt, and let's go this belt. So this would equate to 1, 0, 1, 1. The display will update pretty shortly. And then let's just add 1, 0, 0, 1 to it. So 1, 0, 0, 1. Oh, sorry. Yeah. There is some inversions going on here, but the gist of it is that it still works no matter what you call a 0 or a 1. So in this case, if there is a free flow, that counts as a 0. That allows me later in the circuit to get rid of an inverter, but yeah, so we'll see the display update shortly, and then I'll show some of that circuit in action as well. Yep, so there's our most significant bit here. Same with down here. Yeah, and this design for the display just says if there's flow, we will have a 0. Or if we'll have a 0, and if there is not flow, we'll have a 1. Because this line is always going to be filled, and I kind of just made the display kind of like a 8-bit, a decimal display, but in this case it's only binary, right? So once there's no flow, it becomes a 1. Okay, so now we can go look at the circuit here. So more or less, let's follow the flow here. So this is our least significant bit, right? So that's turned to a 1. In this case, we have no flow. So we can follow this line up. And that is going to our B0 not input. So technically, we're inputting a 0 in my encoding terms. But this kind of is all, I'm expecting an inverted entry, if that makes sense. Okay. So let's see. It's been a while since I've looked at this. I've developed this, I'm not sure how many months back, and then I just never posted about it. So let's see what's going on here. So right now we have no flow, right? And we have no flow on this. So we're getting flow through this gate. So then if we follow it along, so that's the output of one of these gates. And now, because this one is flowing, but this other input is not flowing, we have this output flowing. And then we can follow that around too. And that's this input here. And there's another input that is also a 1. So what we'd expect is this signal to start getting blocked off. And it's almost about blocked off. So you can see that now that there are a lot of frames blocking the way, our signal has turned off. So now we can go down this path and see that now this signal is blocked off. This should start turning on because it is a NAND gate. So in just a second here, see this belt just got backed up, so it will no longer be providing frames. So in just a minute, this should turn on. And this design, I just found online for a full bit adder using only NAND gates. This wasn't my architecture, and it could probably be optimized. For example, I used a full bit adder for this portion. So we have I think we have a C input or something. It's been a while, but I think I had this as a full adder at one point. Yeah, and as I was stating, I believe, well, I've lost track of which one we were following here, but I think it was this input, yeah. So this input is now flowing. This has turned into a 1. Both of these are 1, so this signal will turn off soon. And this is our sum component. So this would be the least significant bit of our output. So let's see if I'm getting this right. Yeah, so that is now not moving. So if we follow this along, I don't lose track of it here. I think I lost track of it. Let's go back here. So this one has stopped moving. Is there a jump? Okay. Okay, and as we can see, this is part of the display as well. It's been a while since I worked on this component, but more or less it just says if they're... Oh man, it's been a while on this one. But more or less this just works for the display. I think it might invert it or something. I've forgotten that piece of it. But as you can see, we're starting to get plates being propagated, which will go into our display here as the sum. So hopefully we can see some of it output. Yeah, and it takes time to propagate, so I think at one point we'll get a bit of a 1 bit turned on here, probably because we turned this bit on first. If you can imagine, this adder is a lot faster than if the signals were propagated based on conveyor belt speed alone. As you can see, these are moving pretty slowly, so we probably wouldn't even had our first input reach the first gate if we were using the traditional full belt equals on, empty belt equals off. And what's nice is we can actually see this thinking a little bit too. So what it was thinking here is one input was on, this one was 0, so it became a 1, but now we're going to have the 0 come on pretty soon. And we also have this input affecting this, so the carryover hasn't propagated through yet. But if you look here, we actually have our most significant bits pretty much done already. We just have this one that needs to change back to a 0, but the carryover for the most significant bit has already propagated, so it already added these two ones together. So this one's changing to 0 now because we added those two numbers, and eventually this will change as well. But while we're waiting on that, I can show off a little bit more about the circuit. So remember how I had the VDD lines? So these are our VDD lines. So this line's whole purpose is always have enough room for plates to propagate. If this gets backed up, it's going to mess up the whole system. This will back up. We'll start having plates go down this line unaccounted for. It causes a mess. So an imperative thing about this circuit is you always need this flow. So what this monstrosity does is it takes these plates and moves them down as far as it can get along this path. So if we zoom out, we can kind of see a triangle shape start to form. So we want to fill up these bottom rows to the maximum in order. And what's nice about this is we also need a voltage source. So what we can do is this line is going to be the strongest, right? So this one is going to be full no matter what. It's at the bottom of the barrel. You know, it all sinks down. So what we can do is we can move this to the bottom of the VCC line. And the goal of this line is to always be able to provide enough plates for any of the inputs. So this is the same concept, but the opposite, where we want this bottom line to always be full. And a little cheat I did was add some storage units as well. So that makes sure all these have a full source of plates at all times and gets filled as necessary throughout. And the reason for as many robot arms as possible here is to fill up all those spaces, especially these barrel ones, so this creates a buffer as well throughout the system. And as you can see, we kind of have it feeding into every single we have more or less power rails from a traditional circuit perspective as well. So this is our power rail for our top two adders. We have our VDD rail for our top two inverters as well. And that same design is propagated here too. And then I also do have an input just in case we need extra plates. So it's flowing pretty slowly. You don't really need that much once the system's going. And same with the VDD line. I do have a few researchers, but like it's not getting any right now even. So overall the system is very stable in the sense that no matter what gets turned on or off, how much power is being used, we should always be able to supply all our gates with what we need. And time to check back in with the addition going on here. So what would we expect so far? 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 0 plus 0 should be 1 here. So we will expect this signal to propagate pretty shortly. And then once that's done, we would expect 1 plus 1 is 10. So that's what we have here. So, oh, and just in time, we have successfully added two 4-bit numbers together. Yeah, this project took me quite a while to build, and this is the second iteration. Yeah, if you have any questions or if you want to try making your own gates based on this concept of movement or not, please feel free to. I'd love to see other designs for this. I only made the NAND because that's all that's really necessary for the full bit adder, but I could see an XOR or an OR or an AND being decently easy to make as well. But yeah, if you have any questions, feel free to leave a comment or post in the Discord. I'll try to keep notifications on if you guys have any questions. And thanks for watching.